All right, guys, this is lesson 7, and this is called magnitude. And magnitude is really how big or how small a number is. Sorry about that. And it is on page 65 of your workbook. So a couple of things, we've realized that the boxes kind of talk about important vocabulary and fact. So fact 1 for magnitude would be the number 10 raised to an n, so some arbitrarily large positive integer n, is a big number in the sense that given a number m, no matter how big it is, there is a power of 10 that is going to exceed it, or exceed m, okay? Fact 2, the number 10 to the negative n for arbitrarily large positive numbers n is a small number in the sense that given a positive number s, no matter how small it is, there is a negative power of 10 that is smaller than s. So really what this is telling us is the exponent of an expression tells us about the magnitude of a number. So how big or how small, and that if it is positive, that it is going to, if it's a positive n, it's going to be a big number. If it's a negative n, it's going to be a small number, okay? So for exercise 1, it says, let m equal, and you have a number in trillions, I believe. So you have 993 trillion, 456 billion, 789 million, 98,765. And the reason we are working with scientific notation is it is an easier way to represent very big and very small numbers. So instead of having to read that, you would eventually, by the end of these next couple of lessons, you'll be able to write in scientific notation. But we're just starting to talk about that here. So find the smallest power of 10 that will exceed m. And so if m equals that, then, and I don't really want to rewrite that, but that right there is less than 999 trillion, 999 billion, 999 million, 999,999. Right, okay, so that is less than that because we have a 9 here and a 3 here in that place value position. Okay, and this right here is going to be less than adding a 1 past here, so into another period. So 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0. Okay, obviously we have a bigger number here because there's more periods. 1 2 3 4 5 6 1 2 3 4 5 and 6, right? And the way that we would write this is equal to 10 to the 15th power. So 3, 6, 9, 12, 15 to get in front of this. So 10 to the 15th power. So let's go back to our question. We're finding the smallest power of 10 that will exceed it. This will be the smallest power of 10 that would exceed it because we're going into another we're going into the next period of numbers, okay? I could also say because m has 15 digits, which is this, right? This has 15 digits. 10 to the 15th will exceed it, and that might make a connection there. Instead of having to write this all out, we have 15 digits here, and so we have 16 digits here, 10 to the 15th power. All right, so exercise 2, and this is kind of an exploratory intro lesson, just talking about big and small numbers. It's not necessarily just I don't know, where you're given purpose, I think. Okay, so we are given to exercise 2. And we have a mixed number here. We have 78,491 and 899 over 987ths, right? And we're trying to find the smallest power of 10 that will exceed m. So if m is that, then what is less than that is going to be 78,492, right? Because this is going to be between 78,492 and 78,491, right? Which is less than 99,999, which is less than 100,000. So we now have more digits, right? We started with 5 digits. Now this is 6 digits. And this right here is equal to 10 to the 1, 2, 3, 4, 5. 10 to the 5th power. So therefore, 10 to the 5th power will exceed m. Okay? So keep in mind how we're looking at that. That has 5 digits, just like that had 15, and it ended up that that was the solution to the problem. Let's go to the back side, where we're now at exercise 3. And exercise 3 says, let m be a positive integer. Explain how to find the smallest power of 10 that exceeds it. So we're just going to explain that. If m is a positive integer, then the power of 10 that exceeds it will be equal to the number of digits and m, just like on the exercise 2 and 1. Example, if m were a 10-digit number, then 10 to the 10th power would exceed m. Okay, and that's an example. Also, if m is a positive number, but it's not an integer, then the power of 10 that would exceed it would be the same power of 10 that would exceed the integer to the right of m on that number line. Like, for example, here's another example of what I just said. If it's not an integer, if it has like a decimal or a fraction, if m is equal to 56 or 5,678.9, then the integer to the right of m is 5,679, right? So it would be 10 to the 4th would exceed it. It's kind of like the second example that we did. It's not like you're considering every single place value position. You're considering the place value positions to the left of the decimal. Okay. And now we're on exercise 4, which we're starting to kind of look at why we are talking about magnitude, what we're going to be doing with it in exercise 4. If you are given a problem that says the chance of you having the same DNA as another person other than identical twins is approximately 1 in 10 trillion. 1 trillion is a 1 followed by 12 zeros. So here we have 1 trillion. Is that 1 trillion? Sorry, 10 trillion. This is 10 trillion. Okay, so given the fraction, express this very small number using a negative power of 10. So this is equal to 1 over, and what we would do is just, how many powers of 10 is it? We're going to take it back to to the left of this last zero. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So then we have 1 and 10 to the 13th power there. Okay, and so even what we wrote there, just take it back to what we were saying. So 10 trillion is a number that has 13 zeros. And so we're saying that it is equal to 1 over 10 to the 13th power, which is equal to, and this is where the negative exponent law comes in, it's equal to 10 to the negative 13th power. Okay? And then exercise 5, which is the chance of winning a big lottery prize is about 10 to the negative 8. Lottery is 10 to the negative 8, and the chance of being struck by lightning in the U.S. in any given year, lightning is about 0.001. Oops, 0, 0. I missed a couple of zeros there. So 0.000001. Okay, so we have 5 zeros. And it says, what do you have a greater chance of experiencing? So it might be helpful to change this back to where we have a power of 10. So 1, 2, 3, 4, 5, 6. This is equal to 10 to the negative 6 power. Okay, so both of these are our chances. And if you're thinking about a number line, keep in mind that there's going to be more zeros between the decimal and a digit. The digit to the far right, if you're writing 10 to the negative 8, there's going to be more zeros than 10 to the negative 6. So 10 to the negative 8 on a number line might be over here, and 10 to the negative 6 might be here, whereas 0 is down this way, and there's positives over here. So when you're looking at what do you have a better chance, a greater chance of happening, that would be this, and this is the lightning, right? So greater chance of getting struck by lightning. Sorry, guys. I know you're tempted to play the lottery, or maybe you will be, but the chances of winning are not that great. Okay, and then we have exercise 6, which is there are about 100 million smartphones in the U.S. Your teacher has one smartphone. What share of U.S. smartphones does your teacher have? Express your answer power of 10. So 1 out of 100 million. Okay, and that is equal to 1 over 10 to the 6, 7, 8, which is equal to 10 to the negative 8. All right, oops, I'm sorry. You might want to pause it now. Okay. And that is that. So in closing, no matter what number is given, we can find the smallest power of 10 that exceeds that number. Very large numbers have a positive power of 10, and we can use negative powers of 10 to represent very small powers that are less than 1 but greater than 0. All right, you could go and do the assessments. Bye.